In this video, we'll be exploring linear functions to represent situations. So in our first example, we're told that the cost, C, in dollars, to produce X number of games is given by this function C of X. And that means that our input is how many games, X, and the output is C of X, which is the cost. So the cost is affected by how many games are produced. As we can see, depending on what X is, right, how many games, it's 80 times X plus an additional $150. The way that this can be interpreted is that it's going to cost $80 per game to produce, since it's 80 times the number of games. This plus 150 can be interpreted in a couple different ways. It might be like an initial cost or a down payment or something like that, or the cost of production equipment. All right, the first thing we want to do is find and interpret C of 10. We know already that that means to plug 10 into this equation, so that'll just be finding C of 10. We'll interpret it after we find it. To find C of 10, we'll plug 10 in for X and see what our output is. We'll have 800 plus 150, which this is in dollars, so it's $950. Once we plugged in 10 for X, we get an output of $950, and so we've found it, but we need to interpret what this means. So we'll interpret just with a sentence. Since C stands for cost, and our input was 10, and the input is how many games, we can imply that since C of 10 is $950, we know that this is the cost of 10 games, the cost to produce 10 games. So our interpretation is the cost to produce 10 games is $950. Okay, so the next thing that we're going to look at is in yellow. We want to know how many games can be produced for 15,000. This is asking us to find the number of games, or to find X. So we don't know what X is. Instead, we know what the cost is. So we're not going to plug in for X. Instead, we know what this output is. It's $15,000. So I'm going to replace the cost of some X, or C of X, with $15,000. And we're looking for the X value that outputted that value of $15,000. So we're kind of solving backwards. Instead of plugging in for a number of specific games, we are given the output Y value of cost, and we want to know what was the X that when we inputted it gave us that 15,000. We'll solve this just like a regular algebraic problem. We'll subtract 150 from both sides, and that will give us, let's see, 14,850, right? Yep. And that equals 80x. Then we want to divide by 80. I'm going to use the calculator for this. And we get 185.625. Now, since we cannot make 0.625 of a game, right, that doesn't make sense in the real world. You can have only an integer amount of games, positive integer amount of games, or 0 games. And so we can't round up because this is not enough money to make 186 games. So to answer our question, we would just say we can make 185 games and that's it. Continuing on with this example, we're going to talk about the implied domain. Remember, the domain are all the values that our input, or in this case X, can take on. Well, if we think about X as what it is, it's the number of games that can be produced. We think, well, we can produce 0 games. We could produce 1, 2, 3, 4, 5, or any number of positive games. The games that we cannot produce, the values that would not make sense for X would be negative values. Therefore, the implied domain, the one that we're assuming is working, is values of X that are greater than or equal to 0. And that's because it does not make any sense to produce a negative amount of games. The next thing we'll look at is C of 0. So This is a find and interpret again, so we will first find C of 0, and that's pretty easy because plugging in 0 is always simple. And when we plug in 0, we'll get 80 times 0 plus 150. So I'm not even going to write that all out. It's just $150. Now, in order to interpret this, this means that we've produced 0 games, and it still costs us $150. So that could mean a couple different things. It might mean that the production costs for the equipment is $150 before we even produce any games. That already costs this company $150. So I'll go with that. We'll say the equipment cost, the equipment to produce games cost $150. We could also say the initial cost, initial meaning the beginning, the initial cost is $150. In business, this might be called your fixed cost or like a startup cost to your business, right? You have to spend money to make money. The last thing that we'll look at is finding and interpreting the slope. The slope of the graph of y equals c of x. So let's just do a quick sketch. We only care about the first quadrant here, and that's because we have a domain that does not have any negative numbers. So I really only care about this quadrant here. And so let's think about what each one of these quadrants is. This horizontal axis is our x-axis, and instead of writing this as the y-axis, I'm going to write it as the cost, or c of x axis. It's our output. All right, so x stands for the number of games. So I'll put the number of games, and then the y-axis is the cost. All right, so we've labeled, and in order to sketch this, we know that our y-intercept is at 150, and that's where we hit the, I'll just make that 150. That's where we start when we're producing 0 games. Once we've produced 1 game, or 2 games, I'll just sketch a couple here, and I could keep going. So 150, I'm going to increase by what the slope is. The slope is 80. So if we add 80 on every time, so we'll have these couple values here. I added 80 on each time. Okay, so we know we start here. Then after producing 1 game, we have 80 times 1, which is 80, plus that initial 150. So we're at 150 and we go 80 more, up to 230. So we have a coordinate point 1, 230. Then if we produce 2 games, right, you can see that we increase by another 80. 80 times 2 this time, plus that initial 150. So we're up to 310. And so on. And 3 games will cost $390. This line will have an arrow this direction, but not in this direction because we cannot have negative amount of games. And we want to find and interpret the slope. Well, the slope's easy enough to find. It's 80. So the slope is 80. And in order to interpret this slope, we'll look and see really what's happening. Every time we go from one point to another point, we see that we're rising $80 and running 1 game, where our vertical change is $80 and our horizontal change is 1 game. So if we interpret it like that, this is $80 per 1 game. Since slope is a rate of change, we'll write it as a rate of change. We'll say that the cost increases at a rate of $80 per game produced. So it's a rate because we use the word per. It's 80 per game, like dollars per game, because our vertical change is measured in dollars and our horizontal change is measured in number of games. This next example gives us 2 points. It says a publisher charges $22.50 to print a 600-page book and $15.50 to print a 400-page book. We want to find a linear function that models the cost of the book C as a function of the number of pages P. So our input, or like our X value, our independent variable, is going to be P, and our output is cost because the number of pages affect the cost. The cost doesn't really affect the number of pages. So just as a quick aside, I'm going to write that we want to remember the coordinate points go P and then C for pages affecting cost. All right, so since we have 2 coordinate points, let's write those out. We have the coordinate point of 600 and 2250, and we also have the coordinate point of 400 and 1550. The first thing that we need to do is find the slope between these 2 points. So to find the slope, we'll do our change in y. So I'm going to do the larger number minus the smaller number, just because that's easier. So we'll have 2250 minus 1550 all over 600 minus 400. This gives us 7 over 200. And just as a quick thing here, this is dollars up top, and this is pages down below. So right now we have that it costs 7/200 dollars per page. Let's make that a little bit simpler to figure out. If we were to divide both of these by 2, we'd have 3.5 out of 100, which is 3.5 cents per page. Since we're in dollars, I will write it as $0.035 per page, but we know that that's 3.5 cents per page. All right, so now that we have the slope, now we can use point slope form in order to find the linear function. I'm just going to use this coordinate point just because the numbers are a little smaller. So when we use point slope form, we'll have y minus 1550, so that's our y coordinate, equals m times x minus 400, since that's our x coordinate, y minus 1550, and then we'll distribute the 0.035 to get 0.035x, and then that times 400 is 14. Then we'll add 1550 to both sides to get y equals 0.035x plus 150. Now I just realized I use x and y out of habit instead of p and c, but that's totally fine. I'm going to replace y with what it is. It's the cost based on the number of pages, p, and it's going to equal 0.035p plus $1.50. And that is our cost function. So it looks like in this case, the cost is $0.035 per page, right? 3.5 cents per page, plus an extra $1.50. The reason that I kept it in dollars and didn't change to cents is because initially the dollars were like the amount used for our y values here. So there we go, there's our linear function. Okay, let's interpret the slope of this function. We know that the slope is this m value right here, and the slope is 0.035, and that is dollars per page. So let's just, as a quick note, it's $0.035 per page. This means that the cost to produce increases at a rate, because slope is a rate, at a rate of $0.035 per page. All right, the next thing we want to find and interpret is C of 0. So C of 0, that's just another way of saying what's the y-intercept, right? Because our input, or c-intercept, I guess, because the input is 0. If our p-value is 0, then that is giving us the c-intercept. So C of 0 is just $1.50. And that tells us that the cost to produce to print 0 pages is $1.50. You could also say the initial cost is $1.50.